Welcome to Quantum Computing Essentials Part 1, Lecture 3. So as we have seen in the previous lectures that we'll be dealing with the quantum states and the quantum operators of the observables, where the importance of vector space is discussed. So today we'll be formally discuss about vector spaces, vector subspaces, and little bit about the inner product space, because all these terms are very much important to understand the Hilbert space and the space of the quantum state vectors. So so regarding vector space, there are 4 things. So 2 sets. So first I will be discussing about vector space. So vector space has 4 things. So 2 sets, let's say V and F, and 2 algebraic operations. Two algebraic operations. So the first operation is known as vector addition. And the second operation is known as scalar multiplication. So I'll be briefly cover all such terms, the definitions and some properties, and the details can be found in the references that I have mentioned in the lecture 1. So there are certain axioms or the certain protocols that a vector space must obey, which include all the 4 things that I have said, 2 sets and their operations. So first is that the set V should be a non-empty set. So it should not be an empty set. So it's a non-empty set. Is a non-empty set. That means there should be some element, non-empty set, okay, of objects, and the objects are called vectors. Okay. So so we say that this particular statement we can rewrite as that this V set is a set of n tuples. So tuples, I think you all know from, it's a computer language term, computational term. So it's a set of n tuples, or a set of, it may be a set of matrices as well. So it should be a non-empty set of objects called vectors. So you can denote the vectors at ket v1, ket v2, and so on. So they are the elements, and they should belong to the set capital V. Okay. So this should this is the first axiom. The second is the second set F, it is a scalar field. F is a scalar field. Scalar field. This is an important term in algebra. I will not discuss it the details. So it's a particular group which obeys certain operations. Okay. So I think it's standard. So F is a scalar field, and we'll come across at a different stage about the vector field of complex numbers, the real numbers, and there are several other fields. But here F is a scalar field, maybe of complex or real, and uh, here F may be either it may be real number, set of real numbers, or it may be a set of complex number as it is a scalar field. Okay. The third property or the third axiom is that um, it follows the vector addition. Vector addition. So so I take two vectors, ket x plus ket y. It is their vector addition, and these two elements, the ket x and ket y, suppose they belongs to the set V, the first set, okay, capital V. So is an operations. This is an particularly operation. The operation is known as the vector addition operations. And this particular result also should belongs to the set capital V. Okay. So if I take two element ket x, ket y from the set capital V, their addition should, the result should be also an element of the set capital V. And the fourth one is the scalar multiplication property. Scalar multiplication property. So what it says that if I take a vector ket x and suppose it's an element of the set capital V, and I take another element which is a scalar element alpha, which is an element of the set F, which may be scalar, complex scalar or the real scalar, then the scalar multiplication operation says that if I multiply alpha with the vector ket x, that is the scalar multiplication of a particular scalar element and a vector, then this particular product should be an element of, it's an operation, and it should be also an element of V. Whereas alpha is an element of F and ket x is an element of V, then this entire result should be an element of V. In addition to this, for properties, there is a formal definitions of the vector space. So the definition is like this. So the set V, this capital V, is called a vector space. Is called a vector space over the field, and here the field is scalar field, okay, over the field F when the following properties hold, okay. Following property hold. So what are the properties? The first property is that the vector ktex that we already are told, that is a vector addition, that should be an element of this the bigger set V, where your ktex and ky, the vectors, they are the element of this set, and their addition should be an element of V. This particular property is also known as closure property for vector addition. Closure property for vector addition. Okay. Second is, this is a very important property, is that there exists a zero vector. Okay. You can denote like this, or you can denote like this. There exists a zero vector as an element of the set V, for which the operation ktex plus ket naught, that means ktex plus ket0, will be equals to the element ktex for all ktex belongs to the set V. Okay. And this satisfy that due to this element, this vector addition property justifies. Okay. So that means you will come across about elements, say for example minus ktex, okay, and plus ktex, okay, and it will result as the vector zero vector. Okay. So this kind of additions is possible because of this element zero vector. Then the scalar multiplication, the alpha into ktex should be an element of the set V for all such vector ktex, an element of V, and all scalar belonging to the set scalar field F, may be complex or the real scalar quantity, the set of real or the complex numbers. And this particular property is also known as closure property for scalar multiplication. For scalar multiplication. So these are the basic requirement or the definition of a vector space, and we will be looking at the much bigger picture, for which we need the term called vector subspace. Okay, so from the term sub, so we have the notion of sets, set and subset. So that is required here. So let a set S is a subset of the bigger set capital V, is also a non-empty set. That means there should be some elements non-empty set. Okay, and is a non-empty set, or we say it's a non-empty subset of the vector space capital V over certain over some field F, over some scalar field F, if S, the set subset S, satisfies all properties of vector space, that means the closure conditions, the closure vector closure addition and the scalar multiplication closure multiplication property, then this S is called subspace, a subspace of the space V, vector space V. That means so for all such elements ket x, ket y, if they belong to the set S, which is a subset of V, then their addition ket x plus ket y should be an element of the set S, and from this property there should be some element ket 0 belongs to the set S to justify all such additions. Means this closure, to hold this closure property for all x and y, there should be an element 0. Secondly, there should be some alpha scalar belongs to the set F such that and some ket x belongs to the set S such that alpha into ket x should belongs to the set S. So these two property must hold for a subspace. So that means a subspace, vector subspace is also a vector space. Okay. So there are certain notes. The first note is that the set Z, that is containing the element ket naught or the zero vector. So containing only zero vector, is a subspace of V of the set V as it trivially satisfied satisfies the closure conditions. The closure conditions. So this ket knot vector is called a trivial subspace of any vector space. Okay, so it's a trivial subspace of any vector space. The second note is that any straight line in R2, any straight line in R2 is it a vector space? Is a vector space or not? So is any straight line in R2 a vector space or not? Okay. So the answer is negative. That means no. Why? So the answer is only the straight lines passing through origin. So all such straight lines, all straight line in R2, so may not pass origin. Okay, may not pass origin, pass through origin. So that means all straight line in R2 may not form the vector space. Only those lines where 0 is an element. Okay, that means ket not, that means passing through origin. All such straight lines will form the vector space. So extending this point to note 2. So I'll write another note. So in R3, in third dimension, the subspaces are so in the 2 dimension, obviously your origin is a subspace as well as all the straight line passing through the origin are subspaces. In R3, the subspaces are the trivial subspace, the ket knot, that means the origin. Then all the lines that pass through origin, they form the subspace, pass through origin. And planes through origin. Planes through origin. So if you see the picture, how will it look like? So if it is a 3-dimensional system, so here this origin, that means this vector ket knot, which has positions 0, 0, 0. So it's a vector space. All lines that pass through this origin, they are the vector spaces. And also the plane. Say for example, I draw a plane in this picture. Um, as such, this particular point is an element of this plane, is also on this particular plane. Then only we can say that this particular plane, this particular straight line and this origin, they are the subspaces in R3. Okay. So typically these kind of planes are known as flat surfaces. So flat surfaces through in higher dimensions. So this kind of surfaces. So if you take some n-dimensional thing, then this kind of surfaces or planes are known as flat surfaces. Flat surfaces. Okay, in higher dimensions. Before going to the fundamental subspaces, which are very much important in linear algebra as well as in the quantum computation theory, so will we see a very important terminology known as span. And together with this span, will be look another term known as spanning set. So now let us consider a set of vectors represented by a set S. S is a set of vectors. Say the vectors are ket v1, ket v2 to ket vr. And which is a subspace of the vector space V. Then the set of all possible, the set of all possible linear combinations, of all such VIs where I is your set 0, 1, 2, R. All the set of all possible linear combinations is called span. So which is given by so it is written as this notation span of the set S. It is equals to or the defined as the set alpha 1 ket v1 plus alpha 2 ket v2 so on to alpha r into ket vr such that all alpha I belongs to the set F and all such V I belongs to the set S for all I. Then this particular set is known as the span of S. So obviously, span of S is a subspace Obviously, it's a subspace of capital V, as it is a linear combination of all elements which are the elements of the subspace S. Then their linear combination is also the subspace of V. So I'm not giving you the proof. You can see in the reference text. So then for a set of vectors, for a set of vectors S, and the elements are ket V1 to ket VR. If V is a vector space, V is a vector space. If V is a vector space such that V equals to span of the set S, we say that S is a spanning set. S is a spanning set for V. So obviously, that means all elements that belongs to this set V should be the elements of S. Then only it is possible. Then only we can say that this particular set is the spanning set for V, the vector space V. Okay. There are two small properties. Let us see this. Then we'll be closing this particular part, and we will go in the next lecture. We'll go for the fundamental subspaces, which is very much interesting. So to define there I'll be giving you a small note, and the note is on the sum of subspaces. Sum of subspaces. So consider that this capital X and the capital Y are subspaces of the vector space capital V. Then the addition X plus Y, X plus Y, and the result will be little x plus little y, element wise addition, such that this little x belongs to the set capital X and little y belongs to the set capital Y. Okay. Then this particular addition, this result should be, it should belongs to the vector space V. And if, so this is one part. And the second part is if X is span X and Sy is span Y, span Y, then the union between Sx and Sy, that should also span the set X plus Y. So these are very basic properties, and they are obvious. In the next lecture, we'll be discussing about the 4 fundamental subspaces, the range space, the null space, which are very much important for algorithm design. 4 fundamental subspaces. And also we'll be discussing about rank nullity theorem. 4 fundamental subspaces and inner product space. These things we'll be discussing in the next lecture. So thank you very much.